Ask Melissa Maribel live. If you are here today, make it known. Say hello in the chat. Tell me how your day is going. So make it known. What this overall live is all about is where you guys tweet your questions ahead of time for a chance to get them answered on my next live show. So far I see Zoe saying hi, hello, welcome. I'm excited to share with you guys everything that I have planned for today. I have Kiki saying hi. I have Asad saying hello, ma'am, hello. And keep making it known, guys, as you guys start to come in. I would love to say hello to you and welcome you. Tanya's saying hi. Brenda's saying hi. So basically saying, hey, I'm here. Magic is saying hi. Zoe's saying I'm stressed as I have mock exams. Mock exams, interesting. I didn't know you guys had mock exams. You might be in AP Chem, I'm assuming, if you're practicing that. And then BT's saying hi. So basically saying I just woke up. Yeah. That's nice on a Sunday, or we're probably in different time zones. Krista Joy saying hello and Kiki saying same. All right, guys. Well, I'm so happy that you all can be here today. We will be going over Dalton's law of partial pressure, mole fractions, and Graham's law of effusion. So don't worry if those are the questions that you guys have. We're also going to be going over the ideal gas law mixed with partial pressures. So that's what we're going to be covering today. I'm so excited to share this this nice little lesson that I prepared for you guys. It was from a question that a student tweeted, and he pretty much asked all of these questions. So I thought, why not? I was getting a lot of questions at this already on gas laws. So I think this is going to be a good thing throughout the lesson to just talk about this. Okay, so and then we'll see at the end. So since Kristen's just saying, can you answer gas law questions on this live stream? Yes. So if it obviously relates to this, which I know it does because it is gas laws, I can do my best and answer towards the end. So I am going to go through everything that I have prepared for you. And then towards the end, I'm fine with answering some gas law questions to see how much time we have left. Okay. All right. So gas laws. Yes, everyone's happy. Why don't we go ahead and start right off? And we're going to talk about partial pressure. So specifically, this is going to talk about Dalton's law of partial pressure. That's what we wanted to look at first. And this is the overall formula that we will be focusing on. So essentially what I want you to think of is Dalton's law of partial pressure is essentially saying this. If we were to have some closed container or some jar or something that's just closed, and inside there are different types of gases, well, Dalton's law is saying that each individual gas's pressure, which is known as partial pressure, is then going to be, if we add them all together, it's then going to be equal to the total pressure of the entire gas mixture. So that's what this formula is talking about. Like, let's say if this is PA, right? So that A, B, C is just representing some sort of gas. So this could be carbon dioxide, this can be oxygen gas, nitrogen gas, and so on. Now, again, it's just telling you it's the sum of all of the different gases' partial pressure is then equal to the total pressure of the mixture. So not too bad so far. That's Dalton's law, but we will also be going over partial pressure, how to find it. So that's going to require something a little bit different. To find, like, let's say we didn't know what the total pressure was and we were asked to find, we were given the total pressure and we're asked to find the partial pressure. Well, this is the formula that we would be using. So this is to find the partial pressure of a gas, and then this is essentially known as mole fraction, a mole fraction. So we'll go over that in a second. And then the formula for this would have been the mole fraction times the total pressure of the gas mixture, which is either given or you find that in like part A or the previous step. And then lastly, we'll also be talking about mole fractions. So what a mole fraction is. So it's represented as this X, and a mole fraction is essentially just the moles of whatever gas you're looking for the mole fraction of. Like in this case, we're going to say gas A, and then it's going to be divided by the total moles in the gas mixture. All right, so that's going to be our mole fractions. So it kind of is like, let's say if you wanted to figure out just the partial pressure, and you note that, okay, well, if I don't have the mole fraction, I have to start there. And then if I don't have the total pressure, I also need that too. So it's kind of like you kind of have to build on it, right? So in case you don't have a specific like mole fraction or total pressure, you do need to know all of these formulas to be able to help you figure them out and then plug them into the actual formula that you need. All right, so don't worry, we're going to do this. These are all the formulas. By the way, all these formulas that I am going over and that you see here, if you haven't already, these are from my chemistry survival guide, which is completely free to download, and that is in the description box of this video. It's actually of every video, so make sure to check that out. I always have resources in all of my in all the description boxes of my videos. What you'll also will see is I do make detailed notes on this topic. So on gas laws, I do have these detailed notes. It's kind of like an ebook where it basically tells you everything you need to know for gas laws. So it shows you all these different types of questions, how they could rearrange or re-ask the question or ask for something else. And it just prepares you. On the screen, you'll see it, as well as it will. The link is in the description box to get that guide, the notes for gas laws. Another little thing that I did want to mention is, in the case that you guys still have more questions, whether it be for gas laws or for something else, and if I didn't answer that, of course, I want to give you guys more resources where you can get more of your questions answered. So in the bottom portion of the description box, you're going to find some of my resources that I recommend. Specifically, the one that I used throughout college was Chegg Study. That was something that was really helpful and beneficial to me. It was kind of like a lifesaver because I didn't understand all my homework, and I know you guys can relate because I got so much homework, and I know you guys do too. So that was just a way to help me understand what in the world I was doing. So it has like step-by-step solutions. So make sure to check it out if you have more questions. For me, it was a good choice for me to have. It was a nice way to just have that instead of, let's say, having a tutor. But of course, if you can afford a great tutor, that's always a great option as well. And they do have online tutoring. So make sure to check that out. As a little disclaimer, if you do decide to purchase Chegg Study or any of those, I am part of their affiliate program. So that just means I do get a small commission, and that just goes to making more videos for you guys. So, okay, let's continue on. Let's start off with the first question. So this first question is saying, a jar contains 425 kilopascals of carbon dioxide, and we have 750 kilopascals of nitrogen and 525 kilopascals of oxygen. What is the total pressure of the container? Okay, so we're given all these different pressures, right? And then we could actually assume that because we're given pressures, and by the way, kilopascals is just a measurement, just a unit to measure pressure. Another thing that you might see, common units are atmospheres, ATM, torr, millimeters mercury, PSI, so pascals. So these are just common ones that you should know. And by the way, in the guide that I was talking about, as well as in my formula sheet or the survival guide, I have all of the different units that you need, or like how to convert different units between each other, like atmospheres to torr and so on. So make sure to check that out because it is really helpful on exams. Okay, so what I want us to think about here is, let's say we were to imagine this jar, right? If we were to have this jar, and this is just representing the entire gas mixture. Well, if we were having this jar, what do we necessarily have in it? We were told that there's carbon dioxide. We also have nitrogen gas and oxygen gas. Well, if we want to find the total pressure of this container, then once again, that's going to apply Dalton's law of partial pressures, where we just add up all the partial pressures, right? So this is essentially what we're talking about here. So in this case, we're just going to look at the partial pressure that was given for carbon dioxide, which is 425. The partial pressure for nitrogen gas, 750, and then the partial pressure of oxygen gas, 525. All right, so literally all you have to do, because all of these are in the same unit, is add everything together, and that's your answer. All right, so that would be your total pressure. So those are the nice questions. Those are the nice ones if we know how to use this formula. All right, so that's how to figure out total pressure, and that's one way to figure out total pressure if we're given all of the partial pressures of the gases in the mixture. All right, but let's say if we're doing something else. So this question is going to be a great test question. The reason for this is because it's going to ask you for multiple things: mole fractions, partial pressure, and how to use total pressure, how to find total pressure while using the ideal gas law. All right, so this is an extremely important example. I do see this on common tests or even just homework assignments or extra credit. All right, so let's start off and understanding what this is giving us and what we're finding. So a 12.5 liter tank contains a mixture of 24.2 grams of helium and 4.32 grams of oxygen gas at 298 Kelvin. Calculate the mole fraction, partial pressure of each gas, and the total pressure of the mixture. Okay, so we're pretty much going to use every single formula that we talked about before, except for Dalton's law of partial pressure. So the first thing that we're going to do, let's just start off with finding the mole fractions of each gas. And we have two different gases that we're going to look at. We're going to look at helium and oxygen gas. Okay, so I'm just going to start off with everything that we're given. I like doing that just to see what we have and what we're going to find. So we have the volume, we have the mass of helium, mass of oxygen, gas, and the temperature. And then we're finding this, remember that X just refers to mole fractions. We're going to find the specific mole fraction of oxygen gas, of helium, the total pressure, and then the partial pressures of oxygen gas and helium. Okay, so mole fractions. With mole fractions, since that's what we're going to start off doing right now, remember that we want the moles of our gas that we're looking for. And the two moles, or actually the two gases that we have, are helium and oxygen gas. So I was given all of our grams, right? So now we have to convert all the grams to moles. That would be our initial step. So I'll just convert both of these grams to moles using the molar mass found on the periodic table. So for helium, the periodic table tells us that it has a mass of 4. So I'm just going to align grams and grams so they can cancel out. And then from there, that gives us 6.05 moles of helium. We'll do the same thing for oxygen gas, just knowing that with oxygen gas, it would have been 2 times the mass of oxygen, which is 2 times 16, which would give us 32. All right, so that's how I got that 32 on the bottom. Okay, and then next, our grams and grams, once again, will cancel out. And we'll get our moles of oxygen gas. Okay, so we have what's on top. So we have our numerator. Here we go. Of our mole fraction, right? We have the moles of that specific gas, of helium and oxygen gas. Now we want to figure out the total moles of the entire gas mixture. So to do that, what you have to do is just add up all the moles of each gas in the gas mixture, which we only have 2 of them, right? So we're going to add these 2 together to find our total moles. So adding those up, we'll get 6.185 moles, and that is our total moles. Now what I want to do is just plug it into the formula. So finding each mole fraction, we found the total moles already. I placed that in there. Those are our total moles on the bottom that we just found right here. Next, what I'm going to do is just put on top, I'm going to put the moles of helium that we found on our previous step, and then the moles of oxygen gas as well. Okay, all we have to do now is divide. So we'll divide these two values. And something that I want to note is that mole fractions do not have any units whatsoever. The reason for this is because our units of moles and moles completely cancel out. So mole fractions are unitless, meaning there's no unit whatsoever. If you were to put the mole there as your unit, it would be marked as wrong. So beware of that. Okay, so we found our mole fractions. That was the first part of this question. And we're going to have to use these again to then figure out the partial pressure of each gas. As well as, we're also going to figure out the total pressure. So the first thing that I want to get to before getting into the partial pressure is I want to jump into how to figure out what the total pressure is. The reason why I want to figure out the total pressure before I look at the partial pressures of each gas is because if we recall our formula, the formula for partial pressure was our mole fraction times the total pressure of the gas mixture. So since we don't have the total pressure of the gas mixture, we need to find that first. So that's what we'll do. All right, so finding the total pressure using the ideal gas law. So I'm going to write this just a tiny bit differently. And since I'm looking for the total pressure, I'm going to actually state that I want the total pressure, P total, and then there's nothing different for our volume, nothing different for our gas constant R, and nothing different for temperature. But there is going to be something slightly different because we do have multiple moles, right? We have 2 different moles. So this would have been N total, or our total moles. All right, so what we need to do now is plug everything in. Okay, so what I did was I just plugged all the values that we previously were given. And we were given our volume here, right, that 12.5. The total moles, we found that in the previous step when we were looking at our mole fractions. Remember, we added up the moles of helium and oxygen gas, and that's what our total moles were here. And then our gas constant is this. So we have two different options. I've seen it either way on exams, or it just depends on whatever your professor's giving you. So I'm going to write it as this constant, but this one would have still given you the same answer. All right, this is just rounded. So I'll plug that in as our R, and then our temperature is that 298 Kelvin. So now we'll multiply this side straight across, and then what would happen is our moles and moles will cancel, and then our Kelvin and Kelvin will cancel, and we're going to be left with just liters times atmospheres. All right, so this is what we have so far. Next up, we want to figure out, we just actually want to get P total by itself. So what we'll do is divide this 12.5 to both sides, and then this is going to cancel this out. This cancels out our liters, and then this gives us our total pressure of 12.1 atmospheres. So that's good so far. Now we're going to keep going to then find the partial pressures of each gas. Okay. So find each partial pressure, and these are the formulas that we're going to look at. So the reason, once again, why we left partial pressure to the very end was because we first needed to figure out the mole fraction of each one, right, of each gas, and then the total pressure. And then from there, we can multiply them together, and we're done. And then that gives us our partial pressure of the gas. So it is knowing how to use each formula. I would definitely say that. And then also just knowing when to use it, right? And how you kind of know when to use it, by the way, is I knew when to use the ideal gas law, that specific one that I was using, because they gave us the volume and the temperature, right? That was like a giveaway. So that's something that I knew to do. And then I knew to leave the partial pressure to the very end because we still needed to figure out the mole fraction and the total pressure of the gas. All right, so those are just little things that you'll be able to pick up throughout. So now for this, I'm just going to plug in everything that we previously had. We found the total pressure and then the mole fractions of each. So plugging in this into the formula, we're going to multiply straight across, and then this gives us our partial pressure of helium and the partial pressure of oxygen gas. All right, so that is what we would get for this overall question. So this is a great question just because it does ask you so many different things. Like I said, I have seen this on different exams. It could even be like, you know, an A through C sort of question, right? Multiple choice, not even multiple choice, just for response. And make sure to know how to use these formulas, guys, because that's going to be something that's really going to be beneficial, especially knowing how to use or even when to use the ideal gas law. And once again, that was when they actually give you the volume and the temperature. Okay, and then you're probably most likely going to be asked to find the total pressure. That's what I normally always see. All right, so that being said, let's move on. And then it looks like I will have some free time. So after this one, if you have a gas law question, I'm fine to help you out. All right, so I'm happy to help you guys out. So Stacy's also saying, hey, Mel, wish me the best of luck today. I have my final chem exam. Oh, wow. Good luck, Stacy. Goodness. A final on a Sunday. That's interesting. Oh, man. But good luck today. Let's keep going on Graham's law of the rate of effusion. So what this is essentially talking about and what effusion is really is, I want you to think of it like a gas is escaping from like a hole, all right? Like let's say if I know this, actually, yeah, sure, why not? My water bottle. So if I were to look at my water bottle and if there were like a small little hole here and all of these, there's water molecules, right? Or there's actually like water vapors. So that's a water gas, like that's our gas. Well, if that's slowly escaping through this hole, then that's effusion. It's whenever those gas particles or gas is escaping through like a hole from a container. It does get a little bit more specific, but what I want you to think of, it's really just when a gas escapes, all right? So that's essentially what effusion is talking about. Now, if we're looking at the rate of effusion, we're seeing how fast that gas will escape, right? So escape from that hole or that container. So That's what I want you to think of when we're looking at the rate of effusion. And that's actually exactly why in the formula, we're going to have our rate of effusion of some sort of gas, which is A, just represented by A, and then it's going to be per the rate of effusion of another gas. So you are comparing the rates. Like think of it as one gas is going to effuse faster than the other, right? So that's why we have to compare or even show this ratio, because it tells us how much faster one gas effuses or escapes. All right, so that's what I want you to think of. And the next thing of this formula, this M is going to represent the molar mass of that specific gas. And then note that it is flipped around. So this is the rate of effusion of A, but the molar mass is going to be on the bottom here. And then the rate of effusion of B is then on top for the molar mass here. So it's always flipped, all right? So that's something to definitely know. If you were to forget this formula, just know that this is A over B, and then the other one is the reciprocal, or it's flipped around, where it's B over A. All right. And then once again, this is the molar mass of each, and we're going to take the square root of that entire thing. All right, so let's do one. Actually, I have two of them. So the first one, an unknown gas effuses at a rate that's 0.462 times that of nitrogen gas. Calculate the molar mass of the unknown gas. Okay. So something further, by the way, that this question can ask you is sometimes they'll ask, what is the gas? Like identify which element or which gas it actually is. And then we would first find the molar mass of it and then look at the periodic table and see whatever's closest to that mass. Then that's your gas, which we can do that with this one as well. Okay, so for this first one, we're using this again, right? This is the rate of our effusion. Now, how do you know where to put what? So the fact that it's telling us an unknown gas effuses, well, the unknown gas is first, so that must be A. So I know, okay, that must be A. That's going to be on top right here, right? That's going to be A. And then it effuses at a rate that of nitrogen gas. So nitrogen gas is second, so that must be B. So N2. And then remember, this is always flipped for our molar mass. So I know that the unknown, the molar mass, is going to be on the bottom, and then the molar mass of N2 would be on top. All right. So all we have to do right now is actually figure that out. So I'm going to figure out what the molar mass of N2 is, because we're actually looking for the molar mass of the unknown gas. And if I were to just look at this on my periodic table, remember that N2 has a molar mass of 28.02, because we're multiplying 2, that subscript, times the actual mass that we found on our periodic table, which is 14.01. So that's what I'm placing on top here. And then you'll note that the rate is already given, because it's telling you that at a rate, right, the unknown gas effuses at a rate, hint, hint, that's 0.462 times that of the nitrogen gas. Well, this is already telling you that it's a rate, and we're kind of comparing them from each other, because it's saying one is effusing faster than the other. So I know that this whole entire chunk is then 0.462, and then all I have to do now is figure out what my unknown mass is. All right, so I have to figure out what this unknown molar mass is. And how I'm going to do that is, remember, this is going back to math, and how do we cancel out a square root? Well, we square both sides. And when we square both sides, then that completely cancels out our square root. And then I still have to square this side out. So when I square that, I get this value. And then when I square the right-hand side, the square root just completely goes away. Okay, what I'm going to do next is I'm going to multiply the molar mass of the unknown to both sides, just to get it on the other side, so to have no denominator. So I'll do that to either side. And when we do that, this cancels out. And that's what I wanted. I wanted those to cancel out so I don't have any denominator. And then from there, all I have to do is figure out what the molar mass of the unknown is by dividing that over. When we do that, our molar mass of the unknown is 131 grams per mole. Now, if this were to ask you, which gas is this? I would look at my periodic table, and the gases that you're typically going to see are your noble gases, most likely. If not, you could also have something a little bit different. I have seen, by the way, beware of this, if you can't necessarily find the molar mass of it, divide it by 2, because it could have been like oxygen gas, like O2 or N2, H2, and so on. So that's something to watch out for. I have seen that on exams as well. But in this case, 131 grams per mole would have been closest to xenon. So that would have been the unknown gas that we see here. Okay. So we have another one for Graham's law of effusion. So it's telling us to find the ratio this time. All right, so a little bit different now. So it tells us find the ratio of effusion rates of hydrogen gas and krypton gas. All right, so now if we're looking at this, find the ratio of effusion rates of hydrogen gas and krypton gas. So if I'm looking at the ratio, I'm still looking at the same question, right? So I'm still looking at the same formula. Now I'm just going to plug in everything that I have. Well, I know that hydrogen is given first. So since this hydrogen gas is given first and this krypton gas is given second, I know that hydrogen gas is then A and then krypton is then RB. And then once again, this is always flipped around, right? That's what it always is in our formula. So then I know all I have to do is figure out or find the molar mass of krypton and the molar mass of hydrogen gas, plug that in and square root this, and then I'm done. So the molar mass of hydrogen gas, remember that's going to be 2 times the mass of hydrogen. So that gives us 2.02. And then if we were to just look at the periodic table, we'll see krypton has a mass of 83.80. So all I have to do is plug that in. When I do that, what I want you guys to do first is divide this after you press enter on your calculator, then take the square root of that value, and that will give you the overall ratio. So remember, ratios are really just talking about fractions. That's why I know that this is the ratio of effusion that they're asking. So this is known as a ratio of effusion as well, of effusion rates. Remember, ratios are really just fractions. So this is our final answer. And remember, it also will not have any units whatsoever. The reason for this is because if we were to take a step back here, and right there. Okay. The reason why there are no units for this is because our units here of grams per mole for our molar mass, those all canceled out. So all of these completely canceled out, and that's why it's unitless. So if we're looking at the overall ratio of effusion rates, or it's pretty much what it's called, we will not see any sort of units whatsoever for that. Okay, so let's see. I have a little bit of time for some more questions, and specifically on gas laws. I know I saw Ryan, welcome back. Happy to see you. I haven't seen you in a while either. I know I believe I talked about nuclear charge, and I want to say a little bit of electron shielding on a previous live session. Yes, I did. So I want to say it was one of my beginning ones. I can see if I can put it in the chat, but I know I do have a video that I did on that. So I can put that here. Because I did want to go over some other gas law questions, since I know that's possibly what I know that's what majority of people want. So this is the time, guys. If you guys have specifically a question on anything gas law related, now is the time to ask it. And I'll see what else I can answer throughout, or see what else everyone said. I desperately need help with understanding calculating wavelength and the amount of energy of a wavelength. I also have a video on that. So for the electromagnetic spectrum, yes, I'll put that video for Ryan first. It was effective nuclear charge. I did go into a little bit of that. And then other than that, I think that might have been it that I have on that section just yet. And then for the previous question was with electromagnetic spectrum. I have a video on that as well. It was a previous live session that I did as well. So I can put that in the chat. And then I see Krista Joy is asking a question. So let me get to that. Okay. So Krista's saying, gas law question we have, and I'm just going to start writing everything that we are given. So we're given the mass, which is 9.98 grams of a pure elemental gas sample is stored in a 4-liter tank with a pressure of 1 atmosphere. Okay. And then the gas is at So our temperature, negative 78 degrees Celsius. What is the molar mass of the gas? Okay, so just looking at all of this, since I'm looking for the molar mass of this gas, the way to figure out which formula you're going to be using is dependent on what you're given, all right? And also what you're finding. But in this case, we're given our pressure, our volume, and our temperature. And those three things are hinting at, well, it can't be the combined gas law because we didn't get twice the amount. We didn't get two pressures, two temperatures, two volumes. And instead, this one is only giving us one pressure, one volume, one temperature. So the ideal gas law must be the case here. So that's exactly what we're going to be using. We will be using PV equals nRT. Now, something else that I want you to think of, because this is finding the molar mass of the gas. Well, the molar mass of the gas, remember what molar mass is measured in for its units. Well, its units are grams per mole. All right, so grams per mole. We have the grams already. That's why they gave you the mass. But we need to figure out the overall moles that the ideal gas law would give us. So that's exactly what we have to do. All right, so what we're going to do first is we're going to use PV equals nRT and solve for N, or the amount of moles. And then our second plan here is then to divide the grams that are given, right, these grams that are given, by the moles that we found in step 1. So that's how you're going to figure out the molar mass of this gas. So let's do that here. All right, so this first part. I don't know what N is, which is okay. That's what I'm going to solve for. And before I actually even start plugging anything in, sometimes it is easier to just rearrange this formula. So that's exactly what I'm going to do now. I'll divide both sides by RT just to get N by itself. And then these cancel, and this gives us N is equal to PV over RT. Now what I have to do is just plug in. All right, so and remember, by the way, R is equal, this is our gas law, constant, gas constant. So this is 0.0821 liters atmospheres divided by moles Kelvin. So I'll plug all of that in, where N is equal to our pressure, which is 1 atmosphere, our volume, which is 4.00 liters, and then our gas constant, we already stated was this. And you're going to note that if we were to plug in our temperature the way that it's at, it would be wrong. And the reason for that is because this gas law constant, this constant, is measured in Kelvin. So we want our temperature to be in Kelvin always for any sort of gas law. All right, so any sort of gas law, when we're looking at this, we want our temperature to be in Kelvin, nothing else. If you were to plug it in, it would give you the wrong answer. And I'm not just talking about the ideal gas law, I'm talking about all gas laws altogether. So what we have to do is convert this to Kelvin by adding 273. All right, so that's exactly what I'm going to do. So 273, really we're subtracting because it is a negative value. This is going to give us 195 Kelvin. And that's what I'll plug in. All right, so the reason why we want all of these units to be the same, right? The same, and what I mean by the same is the same as our gas constant. So the reason for this is because then it cancels out everything that we don't need. So all of our atmospheres are canceling out, our liters are canceling, our Kelvin are canceling, and we're left with what we're actually looking for, which is the amount of moles. So let's do that now. I'm just going to divide 4 divided by the bottom multiplied, and we'll see what we get. All right, so N is then equal to 0.24, and I'm going to actually round to 3 sig figs, so 9. Actually, I'm going to round up just because it's 985, so I'm going to round up to 50 moles. All right, so we found the moles. The next step is to then divide. We're given our mass already, and I'm going to put this over here. So we're given our mass of 9.98 grams. Molar mass is grams per mole. So I'm going to divide this by the moles that we just found. So that's 9.98 divided by 0.250. And then this is going to give us, which I'll state here, 39.9 grams per mole. That would be the molar mass of our gas. All right, so that's the main thing to look at these types of questions when we're looking at molar mass of the gas. I have also seen them ask for the density of the gas. What I recommend you guys do is, one, identify what you're given. That's always going to help you, especially with gas laws. Understand, what am I doing? Like, what formula am I going to use? It typically gives it away because it only refers to two different things, or if it has all three, then most likely it's the ideal gas law. And by all three, I mean pressure, volume, and temperature. But if it were to just have, let's say, volume and temperature, then I know I'm using Charles' law. Then if it has only pressure and volume, and there's two different pressures and volumes, then I know that's going to be Boyle's law. So that's something that just helps you know instantly what formula to use. All right, so, and then for this one, by the way, how I knew what to do was also by looking at the units of molar mass. The fact that molar mass has grams per mole, I instantly knew I must find the moles first. And because they gave me the mass already, I then just divide those and I'm done. All right, so I do have another question from, let me see if I can clear all this while I do that. I do have another question from Christine, and I think I actually have one more slide. Oh, come on. I think all of this, there we go. Okay. Yeah, I should have one more slide. I don't. Okay. There we go. Okay, cool. So Christine's asking, how do you know which one is a constant? Such as P1, P2, V1, V2. Which one is a constant, or which one is held a constant? And with the formulas, how do you adjust the formula of that? Give me a second. What, does that make sense? I see. I believe your question is, how do you rearrange formulas? Right? Let me know if that's what you're thinking, but I'll do the for example part. But this is what I understand of the question. Let's say if we're trying to find T2, when you're given, hold on, the combined gas law. Yeah. I believe I understand your question. So let's say if we're given this. Okay. If we wanted to rearrange this, since we're not given any values, let's just rearrange it and I'll show you how I would have done this. So when we have two different fractions, the easiest way that I have always felt was cross multiplication, because everything is already being multiplied. Like these two are multiplied, these two are multiplied. So if I were to just cross multiply, what this does is this is going to completely remove the fractions or the denominator. And then just note in the blue, what we're doing here, it's really P1 times V1 times T2. And then in the green, you're going to see it's the similar case where it's P2, V2, and T1. All right. So then from there, I know, okay, well, I'm looking for T2. And if all of this is being multiplied, then what's the opposite of multiplication? Division. So I'll divide both sides by the things that I don't need, which is P1, and V1. And I'll divide that over just so I can cancel. And then from there, I solve for T2. So T2 is then equal to P2, V2, T1 divided by P1 over V1. All right. Does that make sense, Christine? Does that answer your question? Let me know. But that's what I would have done for any sort of fraction in this case. And it's just cross multiplication. It makes it a lot simpler to solve for. Okay, let's see if we have any more questions on gas laws. So that's relating partial pressures, any sort of gas law question, whether it be finding the molar mass density, and so on. So let me know as I clear this out. But I think there are some other questions which I can recommend you to another video. Let's see if I'm missing anything. I see Yusuf saying, hello, Melissa. I'm a freshman in high school and I have a quiz tomorrow and I'm having trouble finding the Roman numeral and ionic and covalent compounds and the formulas of the names. So, for Yusuf saying needing help with naming compounds specifically for ionic and covalent, I do have a lot of videos already on that. I can put in the chat the different videos, and I actually have a playlist, I believe. I do have a playlist on naming compounds. So I'll put the naming compounds playlist there. That's going to be very beneficial because I do go over a lot of examples going from the compound name to the chemical formula and back and forth, and I do discuss Roman numerals or transition metals. All right, so that's going to really help you out. But I'll put that in the chat now. And then, let's see. I can see what else. Do you have notes on gas laws? Yes, I do. So, and I think that we just put it in the chat, but I do have notes on gas laws. They do go into a lot of detail. So basically everything you need to know about gas laws, and that's literally how to use every single gas law, as well as how to use Dalton's law of partial pressure, and whether it be if you're finding the molar mass, if you're finding, goodness, I have like every variation. If you're finding the density, if you're finding partial pressure, mole fractions, and so on. I have put every single possible thing that I can think of or I have seen on exams in that gas law notes. So I just put it there. All right, so a lot of these questions that I am getting are not on gas laws, guys. So I do recommend, like for oxidation numbers, I have a video on that. I do have one where I was talking about balancing redox reactions, and I explain oxidation numbers in the very beginning. I even explain how to balance redox reactions and more on redox reactions as well. So I'll put that in the chat. How do you know if an element obeys Lewis? I have a video on Lewis structures as well. So I'll also put my video on Lewis structures for that in the chat as well. So as for, and I am going over just things on gas laws, Samantha, but I do have a video that can help you with that solution question. It is my molarity and solution stoichiometry video. So I'll put that also in the chat, guys. I pretty much have almost everything, I'd say, on the videos I've already made. So always make sure to check out what I have, because there's plenty of helpful videos there. So I'll put the redox reactions video, and that was the balancing one, and with the oxidation numbers. And the Lewis structure, I'll also place that in the chat now. Lewis structures, formal charges, and resonance. It's a previous live that I did. I'll put that in there too. And then as for Brenda saying, can you do an example of gas laws with density? Sure. Let me get this a little bit clearer. Don't have one on me right now, but I can see if I can make it up and just give you an example off the top of my head. Okay. So for density, come on. Let's say if the question is asking you for density, and we're going to figure this out. And oh, by the way, there's one more little video that I wanted to put in for Samantha. It was for molarity, and it was solution stoichiometry. So I'll put that in the chat for you as well, Samantha, so that will be helpful. Okay, so for density, remember that density, let me get back. Okay, so for finding density, remember density's units are grams per liters. It's some sort of mass per volume, right? And if, let's say, we were given that our mass was, I'm going to use that again, 9.98 grams of some sort of gas. And we were also given that our temperature was, let's say, 25 degrees Celsius. And our pressure was 1 atmosphere. And we're asked to find the density. All right, so let's just say that's all that it gives us. All right, so what we would do first is the fact that, well, I know I don't have volume, right? And I need volume to find the overall density. Well, this is a specific type of question where you're actually going to have two unknowns when we're looking at, and hold on, I would need one more thing for this question. If I'm looking for a gas, let's say this is helium. Sure. I'm just making this up as I go. Okay. So let's say this is of helium. All right, now this is going to work. So if I didn't have, let's say I don't have the moles, right? I don't have the moles. I also don't have the volume. So what I'm going to do in this case is this. I'm still going to use PV equals nRT. But I'm going to do this a tiny bit differently where I'm actually going to solve for N over V. And the reason why I'm doing that is because I would then find, and actually I wouldn't even have that this is helium. I would actually have the molar mass of the gas. Let's say that's 4.00 grams per mole. Yeah, that's what I would be given. So the reason why I want to do this is because I would have moles per liters, and then I got closer to liters. And then from there, I can then use the molar mass given, and I can then convert that to grams over liters. So don't worry, we're going to do it. So all I want to do first is, just because I'm not given the amount of, I wish you could erase with this thing, but you can't. Just because I'm not given the moles or the volume, I have to solve for N over V. So that's what I'm going to do. So what I'll do is I'll divide V to both sides. So now I have my pressure. This is nRT over V. And then I just want N over V. So what I'm going to do is multiply by the reciprocal of RT, which is the same thing as dividing RT over. This cancels. And now I'm left with P over RT is equal to N over V. Okay. Now I'm just going to plug everything in. Well, one thing to note is the temperature in Kelvin? No. So I would have to add that 273. That gives us 298 Kelvin. Now I can just plug everything in and solve. So there's 1 atmosphere on top. Our gas constant is 0.0821 liters atmospheres divided by moles Kelvin. And then our temperature was 298 Kelvin. So once again, this is equal to N over V. So you're going to note that your atmospheres and atmospheres cancel and your Kelvin and Kelvin cancel. And if we were to flip the liters and moles, this will give us moles divided by liters, because this is really 1 over, this is the opposite. This is 1 over liters over moles, which is we would then flip it and it would have given us moles over liters. So if I do this math, let's see what we get. 298 times our gas constant. That gives us 0.041 moles per liter. And what I'm going to do now is, and let's see if I could erase it this way. What I'm going to do now, if this quickly does it, is I want to use, and I'll just do it here. Sorry, guys. Okay, so I want to get grams over liters, right? That's the whole goal. And I realize I still wouldn't even have this mass. You'd be given the molar mass, and you'd be giving temperature and pressure. Yes, that's what the question is. So what I'm going to do is I'm just going to multiply by the molar mass of the given question. So this would have been 4.00 grams per mole. Our moles and moles will cancel, and we're going to be left with grams per liter. And then that's how I knew to stop. All right, so there are different types of questions there with density. As I mentioned, guys, in the gas law notes that I did create, I do have several different variations of how to find the density of a gas. There are 2 different ways. This is one of them, but ultimately I do put all the different steps there outlined to make it a lot simpler. But this is essentially what you would do for this type of question is you would find N over V. From there, if they gave you the molar mass, which they most likely will, they have to in this case, you would multiply that, and then you'd get your units of grams per liter. As you can tell, units are extremely important. They're going to help you understand what step to then take next. So, okay, guys. So that's pretty much what we have today. We did go over several things. I did want to mention real quick is that I know this coming Sunday is towards the holidays, so I will not be having a live just because I want to spend time with my family, and I'm sure you guys also want to spend time with your family for Thanksgiving as well. So next Sunday's live is canceled, but I will continue for the following week. For that Sunday to then get you guys, to help you guys out, because I know finals are soon approaching. So, of course, I'd say don't tweet me throughout this week, but the following week, make sure to tweet me your questions at Hello Melissa M on Twitter, and then use the hashtag of Ask Melissa Maribel. If you guys, of course, have other additional questions, and if I don't have a video or any resources on it, or if you just want that exact question answered, then I do recommend something called Chegg Study. You'll find that in the description box towards the bottom. There's a link there. What Chegg Study is it's step-by-step solutions. So if you do have a question, you can either type in and see what, actually a lot of them already have the question that you're asked, because there's like so many questions already in their bank of questions. Or you can literally just ask a question, that specific question, and a tutor will then answer it in like a step-by-step manner, and it explains everything really nicely. So make sure to check that out if you still have additional questions. Okay, guys. So that being said, I hope you guys have a great Sunday, and I hope you guys have an amazing holiday. Happy Thanksgiving. A little bit early, but happy Thanksgiving. And for everyone who has exams coming up this week, any finals coming up, good luck. Keep studying. Keep going. You can do this. All right, guys. Have a great Sunday. See ya.